Welcome back. So, in today's video lecture, we will look at the deposition of Langmuir Blodgett films and a tutorial session on adsorption from solution. Okay. So, in today's video lecture, you will understand the process behind the Langmuir Blodgett trough. Okay. The types of various LB films. Okay. And you will also understand about what is known as surface pressure versus area isotherm. So this data between the surface pressure area isotherm will be very useful for us to understand about the molecular packing. Okay, if you want to understand what is the one molecule thickness, right? Molecular area or the one molecule thickness. If you want to understand, one can deduce the information from the surface pressure versus area isotherm. And if you want to understand about the collapse pressure, you can use this information. And if you want, sometime if you want to understand the molecular weight of unknown compound, we can actually obtain the data from the surface area versus isotherm. That is exactly what we are going to look at in today's lecture. Let's begin our lecture. Yeah. So as we just spoke about, so LB film, and we'll also look at the tutorial from the adsorption from solution. Okay, we'll look at one exercise in today's tutorial. Okay, and so first let us look at the learning objectives for today's lecture will be, we will understand about the different types of monolayer, the process behind the LB technique, surface pressure versus area per molecule isotherm. These three things we will look at in details. So first let us understand what are different types of monolayer that we know. We already spoke about the Gibbs monolayer in previous lectures. So in the case of Gibbs monolayer, what you will be doing is you will be employing the surfactant molecules in the bulk, okay, which means that these surfactant molecules are soluble in the medium that you have chosen, and so the moment you add these molecules into the bulk, they will go to the interface and they will adsorb at the interface, right? So they have a tendency to go to the interface and adsorb at the interface, and as you add more and more molecules into the bulk, more and more molecules will also go and adsorb at the interface. At some point you will see that there are the molecule they have reached the saturation level, which means that any further addition will result in the formation of the micelle. This concept we have seen in the previous lecture. So the monolayer of this form is not, obtained from this process is nothing but Gibbs monolayer. Okay, so when I say monolayer, when you measure the thickness of this from the bottom to top, okay, covering up to the top of the tip of the tail, you will get the one molecule thickness, right? So that is why we call it as a monolayer. And the second type is nothing but Langmuir monolayer. So in this case, unlike the Gibbs monolayer, we will not be employing the surfactant molecules in the bulk, because the solute that we choose may not be soluble in the medium that we work in the like for example, this will not be, let's say if you choose water as a medium, this molecule will not be soluble in the water, right? As in the so in such case you can achieve what is known as the Langmuir monolayer. So in this case you will actually take these molecules, surfactant molecules, into a suitable organic solvent, like for example you can say for example stearic acid in chloroform, right? So chloroform will be in a volatile solvent as soon as you add the surfactant molecules. So you will have to spread these molecules nicely at the interface, right, using some syringe, right? So you will have to use employ micro syringe, and a known concentration of a known volume of the solution will have to be spread from the top close to the interface, right? So as soon as you spread these molecules, chloroform will be evaporating, okay, leaving behind the surfactant at the interface, right? So if you take too much of concentration, so you will reach a stage where the molecules are very closely packed. Okay, when they are very closely packed, you will achieve or you will attain a state where they will be oriented in this fashion. So you will what you will get is the one molecule thickness, a film with the one molecule thickness. This is nothing but Langmuir monolayer. Okay, so the other type of monolayer is Langmuir-Blodgett monolayer. It is very simple. It is same as the Langmuir monolayer, but you will also have to include another module within the trough, which we will see later shortly. So using that module, you can actually lift or transfer these film onto any suitable substrate of your interest. So it can be a glass substrate, it can be mica substrate. So you want this molecule to stand at the solid surface, so that you want to use them for some application like optical applications, electronic application and things like that. So such film is nothing but Langmuir-Blodgett monolayer film, right? So we will look at the various components of the Langmuir trough first, then we'll understand what is Langmuir-Blodgett. So Langmuir, when I say Langmuir, it is nothing but a trough, right? This trough is made up of the Teflon. The reason is you can get rid of the issues like dust and all those things. So dust formation can be eliminated, and cleaning will be easier, right? When you make trough out of the Teflon, using the Teflon. And you will also have a barrier, okay, which is nothing but there will be double barrier system, a trough attached with double barrier, and these barriers will be connected with the motor, okay. So this barrier can be moved, okay, towards each other, and they can be moved away from each other. They can be pulled away from each other. So in this way, when you move close to each other, towards each other, they will be compressing the so you will perform the compression isotherm, right? And when you pull them apart from each other, you will perform the expansion isotherm. So in this way, you will actually perform this experiment. Okay, in the trough, you will have to fill up this trough with the suitable subphase. Subphase here is the purified water, okay, and usually air water interface. So you will consider there will be air above the water, and because subphase is filled with water, you can create air water interface, and you can spread these molecules nicely at the interface. And when you perform the compression isotherm, what will happen is initially the molecules will be wide apart, which means that they will be orienting, they will be lying flat at the interface. So in this fashion, now as you move the barrier close to each other, the orientation of the molecules will change from this state to they'll get tilted up. I mean, the tail part will get aligned vertically as you move the barrier close to each other. So you will reach a state where they are completely packed, okay, they reached a condensed solid state, and beyond that you cannot compress them further because they occupy all the area given in the trough, right? So after that you will so when you transfer these film using the dip coating module, which is the additional accessory which comes along with the trough, so you can transfer this monolayer directly onto the substrate of your interest, okay. So this is how the entire process is done. Okay, so there are various components essential, if you want to operate this trough. So various components are there, like for example, the trough is very essential, right? And you will also have what is known as the Wilhelmine plate, which is made up of some special alloy, and that will be connected to the the balance, micro balance. Okay, and micro balance will be connected to the control unit, and there will be an interface between control unit and the motor. Okay, so you can actually control the motor speed, control the distance, okay, up to which this barrier barrier has to move. And you can also control you can set the surface pressure and all those things. Okay, decide, you can set the surface pressure to the desired set point. So there are various controlling parameters that you will understand later. And this is the monolayer film at the interface, right? So this is nothing. So here we have shown one architecture, that is Y type film. So you have three types of LB film that can be formed. So one such film is the Y type film. So here you will obtain the film in each cycle. For example, each cycle consists of dipping and lifting process, right? When you dip and lift, you will actually carry along with the substrate two monolayer, right? So when you obtain two monolayer in successive strokes, you will be achieving the architecture close to Y type film in this way. That is like tail to tail and head to head arrangement. So you will see there is head to head and tail to tail arrangement, right, in this case. So this is possible when you perform or when you achieve film at every cycle, at each stroke. That means when you lift, you pick up a film, and when you dip also you pick up a film. In this way you will get the Y type film deposition. This is one type of architecture that you often come across when you use the LB film. Okay, and when we talk about the LB film, you should also know what is known as the surface pressure. Like we can relate this surface pressure to the pressure in the conventional system, in the bulk phase, right? So here you will the surface pressure is defined as the difference between the surface tension measured in the absence of monolayer or in the presence of monolayer. Say for example, at initially, because the molecules will be in a gaseous state, they will be wide apart. The surface tension will be same as the surface tension in the absence of monolayer. So this will be zero, almost zero. So you will start the surface pressure, you will start with the zero, and as you compress the monolayer towards as you push the monolayer barrier towards each other, this monolayer will be compressed, right? So this orientation will be changed from the horizontal orientation to the vertical orientation, right? In this fashion they will reduce the surface tension to the maximum extent. So you will achieve surface tension the surface pressure close to the surface tension in the absence of the monolayer. So you will reach so you will start from zero and you will reach up to this point. So this point is nothing but your collapse pressure, and most likely you will reach this state, that is 72 millinewton per meter, if you go up to the collapse pressure, because there is no further change in the surface tension when you reach a point, right, maximum distance, after which there will be no change in this component. So you will see that the surface pressure is same as the surface tension measured in the absence of monolayer, right? So usually you will have to employ the amphiphilic component, surface active component. It will have both hydrophobic and hydrophilic. Okay, and there are some physical variables such as temperature is affected. So your process is affected by the temperature. area of the water surface and number of molecules, the concentration of the solute that you spread across at the interface. So here you can see very clearly how it is measured. So basically what you will do, you have the monolayer and you have the barrier system. So initially when you connect the Wilhelm plate to the microbalance, what will happen is they measure the weight acting on the plate, right? That is the reference point, right? So that will be the maximum. Okay. Now as the barrier is pushed and compression isotherm is performed, the monolayer will be arranged in the fashion like the way it is displayed here. In that case, it will reduce the surface tension to the maximum extent possible. At that point, the weight acting on the plate will be changing, right? Will be decreasing, because as the more and more as the molecules change their orientation, the surface tension acting, the weight acting on the plate will change, because surface tension will be lowered, so the weight acting on the plate will also be lowered. In such case, so whatever you monitor is basically the weight acting on the plate, right? So once you know that, we know it is easy to calculate the the surface tension, right, using this formula that we have already seen. So in this way you can calculate what is gamma, because the Wilhelm plate is usually made up of the pure, some special alloyed material. So theta is usually negligible, which means that cos 0 will always be 1. So you can easily measure gamma as W by P itself. So the W will be changing as the barrier is pushed towards each other, okay, as the area is changing, right? So in that way you can actually get the the surface pressure versus the area per molecule isotherm. So this is why it is called area per molecule isotherm, okay, right. So this is in the modern day, you will have this tuff attached to the microscopy. It has the it has got the advantage is twofold. One is you can actually generate surface pressure versus area isotherm, area per molecule isotherm. This is one advantage. Another advantage is you can also understand, visually see, distinctly see the molecules, the morphology of the compound, that compounds absorbed at the interface, right? So as they go from gaseous state to liquid state to solid state, you can understand their the structure by visually imaging them using some fluorescent microscopy. So if you have to, if you fluorescently label the molecule that you want to see, and if you spread them at the interface and perform the the compression isotherm, you can directly look at them visually also in situ, how the morphology, how the structure is going to be, right? So this is the advantage of the trough attached with the microscope system, right? So as you know, as you perform the compression isotherm, the molecules are experiencing going from one state to another state, like initially, because the barrier is too much apart from each other, the molecules are too much away from each other, right? So which means that, so they will be at the interface, but the tail will be lying flat at the interface, right? So in this way you can say that they are not active at the interface, okay, because they are in the gaseous state, right? And then as you move the barrier towards each other, they will be going from one state to the another state, which is gas to liquid expanded state, then liquid condensed state, then you have solid state, After that, you will reach the point where you will reach the collapse pressure, okay, because there is no further scope for compression. So you will reach the the saturation. So that point is nothing but your collapse pressure, right? So this is how you perform the surface pressure. You collect the surface pressure versus isotherm data. So the advantage, another advantage is how you can measure the molecular weight of the unknown compounds. So we know that for gas molecule, you can use this ideal gas relation, which is nothing but PV is equal to nRT. Now we are talking about the not the bulk phenomena, we are talking about the interfacial phenomena. So since we are talking about the interfacial phenomena, so this PV term can be replaced with the pi and A term, surface pressure and area, per molecule term. So in this case, you will have to measure the pi surface pressure and area, which is nothing but nRT. You can also obtain 1 by n as RT by pi A, or m by n as mRT by pi A, or you can also say m by n as RT by pi A by m. So this is nothing but area per mass per gram of the molecule that you have spread at the interface. So if you know this information, that is pi versus area per mass, or if you know area the area corresponding to the pi, right, and divided if you normalize that area with respect to the mass of the sample, you will get the pi A by m, right. In this way you can actually obtain what is the molecular weight of the unknown compound. For this, one assumption, one important condition is, as you know, ideal gas is valid in this limit, that is P tends to 0, right. So in this case, you have to choose the pi very close to 0, right. So when you choose pi very close to 0, the area corresponding to that can be measured, and pi corresponding to this tends to 0, very close to 0, can be measured, and this data can be substituted here, and you can calculate what is the unknown sample, molecular weight of the unknown sample. This is one good approach, although you may not get precisely same as the chromatographic technique, but this can be a complementary technique. You can measure sometime, use this data to measure the molecular weight of the unknown compound. So these are various type of film, as you know. So you have X type, Y type, Z type, okay. So Y type is something you will achieve film at every stroke. That means you will have a dipper, okay, attached to the trough. So whenever you perform the dipping or lifting at both the stroke, every cycle will consist of 2 strokes. One is the dipping and the lifting. Both the stroke, when you perform during the dipping and lifting, both the operation, both these operation, dipping and lifting operation, you will get 2 layer. So one is initially your substrate. If the substrate that you use, if it is hydrophobic, when you perform the dipping, let's say you perform the dipping, you have the molecules here, okay. So you have to perform the dipping. When it comes push towards downward, because substrate is hydrophobic, it can pick up this layer, because this is also hydrophobic. The tail part is hydrophobic. You can easily transfer this molecule onto the glass substrate, because there will be hydrophobic, both will be attracting each other. So in this way you will get the first monolayer, right. When you perform the lifting again, you will again lift the second layer, because so through the hydrogen bonding as well, you can achieve this kind of the second monolayer, right. So there will be so when you, in this way, if you perform the cycle multiple times, you will achieve the film will grow in this fashion, like tail to tail, and head to head will be arranged each other, right? Yeah. So this is X type film and this is Z type film. X type and Z type will be, you will be getting film only during only one stroke. For example, X type will be you will be able to achieve only when you perform dipping, whereas Z type you will be achieving only when you perform lifting, right? So depending on the nature of the substrate, you can actually pick up the film, and the arrangement of this film will be changing according to the nature of the film and nature of the the substrate, right? So in this way one can achieve Z type, X type and Y type. So the application, so as I have listed here, you can it can be this LB can be used for several applications ranging from interfacial property to anti-reflective close. If you want to prepare anti-reflective glass film, you can use the LB using this fluorinated organic film. And if you want to develop the glucose biosensor, you can use this compound, that is the thiophene compound. Using the LB film you can achieve this biosensor film, and you can also develop the UV resist film based on this compound using the LB application, right? These are various applications of LB, Langmuir block gate deposition, right? So today's tutorial is going to be how you can calculate the excess, surface excess, right? And the data has been given, gamma and C data has been given. So we know the surface excess of solute is nothing but C by RT d d gamma by dc. So this is our formula that we obtained when we derived the Gibbs adsorption isotherm. So what we need to know is the d gamma by dc. When you know d gamma by dc at a different concentration C, you can calculate what is the surface pressure, right? So for that, what we will do, here you can see this Excel file. So this is the data that we have, C versus gamma data we have. When you plot this data, you get the straight line, okay, with the slope negative. So when you get the straight line with the slope negative, it will be a positive surface excess. So here the slope is minus 50, so which is nothing but d gamma by dc. The slope is nothing but d gamma by dc. When you substitute this value, that is minus 50.88 in this, and C that is 0.1 and 0.25, you will get the data, like what is the surface excess, right, for 0.1 and 0.25, right? So the surface excess at a concentration of 0.1 is nothing but 2 millimole per meter square. So the surface excess is nothing but N by V, so N by A, so moles per meter squared. So the surface excess at 0.1 is 2 millimole per meter square, and at 0.25 is 5 millimole per meter square, okay? 5 millimole per meter. Okay, so in this way you can calculate what is the surface excess, and so I think it will be more clear to you as you do this exercise yourself. We will stop here. We will continue from the next lecture. Thank you.